This video is on gas stoichiometry, and specifically gas stoichiometry in which a gas is being collected over water, which is a common way of trapping a gas. The process is very simple. For example, if you were to heat KClO3, which is potassium chlorate, it will decompose into solid KCl and oxygen gas. And what you can do is, you can trap that gas. And what we'll do is, as the gas evolves, it will move up, forcing other things out of the way, and it will start to bubble. It will start to bubble through this liquid right here. But what you can do is you can take a cup that's filled with liquid and put it over the top like so. And if that cup was already filled with liquid, let me put that in there, so, like so. What will happen is the liquid that's in this cup will slowly get displaced with oxygen and move down like this. And so you can trap your oxygen here, and because it was collected over water, you know it's just oxygen. Now, in the olden days, they would do this with mercury, which would lead to less issues in terms of what's called vapor pressure, because there's a problem inherent in this if you're actually trying to do quantitative analysis, and that is some of the pressure in that container is caused by the oxygen, but some of the pressure is also caused by water, because even though it's below the boiling point temperature of water, some of the water will have evaporated. So imagine you have a situation in which you want to, let's say, go backwards and determine, based upon the amount of oxygen that you have collected, what mass of KClO3 you decomposed in the tube. Maybe it was a mixture, maybe it was only partially decomposed, but you want to know for some reason how much actual KClO3 decomposed. Well, imagine you've collected the space that the oxygen takes up is 2.00 liters. So you know the volume that the oxygen takes up, but there's water in there too. Now, oxygen fills up the whole container. So we're going to use this volume. That's okay to use. We can use the temperature in our calculation. We know it's 295 K, and that's already in Kelvin, so we're good with our temperature, right? And now we got our pressure issue, right? In case you may have forgotten this, but in high school chemistry, 10th grade chemistry, you had temperature and you had vapor pressure on this axis here, and water went up like a curve like that. You can look these up, okay? And you can find, if you look up the temperature of 295 K for water, you'll find the vapor pressure of water at that particular temperature, okay, is approximately 21 torr. Now, that means we can figure out what the pressure caused by the oxygen was, because if you think about it this way, the total pressure, which we already know because we probably took with a barometer or looked up the atmospheric pressure, was 758 torr, right? That's equal to the pressure caused by the oxygen plus the pressure caused by the water. If we look up the vapor pressure of the water, we can literally just subtract that 21 torr from there. And if we take 758 and we subtract 21, we get the value of 737 torr. And that basically is equal to P of O2. And now that we have that value, okay, we can convert that into atmospheres and plug the values that we have into PivNert and determine the number of moles of oxygen we have. So let me just reiterate here what we're doing here. The goal here was really to get the number of moles of oxygen. Once we get that, we can go back and get the moles and the grams of the original reactant. The problem along the way is we have to take into account the pressure caused by the water. Both the water and the oxygen fill the entire volume. So the volume is set at 2 liters. Even though there are 2 different gases in there, the oxygen does in fact take up the 2 liters. So we're going to do a quick conversion here. We're going to take our 737 torr, right, and which is the same as millimeters of mercury, and we're going to take that and divide that by 760 torr is 1 atmosphere, and that's going to give us our pressure in the unit we prefer to have, which is atmospheres, because that's what our value for R is. Although we could also convert R, so the value of that is in torr. So we get 0.969 atmospheres of pressure was caused by the oxygen. And now we can just plug that into PivNert. And I'm going to just reorganize it here. So I'll have N equals P times V over NT, right? So I've just moved RT, right? And so the N's over there by itself now. Okay, so let's put our values in here. So when we do this right now, we get 0.969 ATMs times our volume, which is 2.00 liter, over the R value, which is 0.08206 liters times atmosphere mole Kelvin. And finally, we can times that by the temperature, which was 295. When I do all that math, I get a value of 0.0801 moles of O2. Because remember, this was for the O2. This was the N of the O2, right? So we were solving for the moles of O2. And now we're back to a very, very simple stoichiometry question, because we now have the moles of the oxygen. We can get the moles of the KCl3, and therefore we can figure out what the mass is as well. So now we can take the stoichiometric proportions in the equation and go for every 3 moles of O2, there's going to be 2 moles of KClO3. And then we can take that, and that will give us moles of KCl3, and basically multiply that by the formula mass of KCl3, which I looked up before. It's 122.6 grams is 1 mole. And now we can just multiply those values out. So I'm going to pause and do that. So the final value I get here is 6.54 grams of KClO3. So this is one type of stoichiometry. The key thing is whenever you're collecting over water, there's this extra little step here, and the step is to subtract the pressure of the water from the total pressure to get the pressure of the gas of interest, and from that you can then use Pivner to get the moles, and then you're back in basic stoichiometry again.